Could 3D printing finally end the organ transplant shortage? The organ shortage crisis is a silent epidemic. Every year, thousands of patients find themselves on lengthy wait lists, anxiously hoping for the gift of life through a transplant. In the United States alone, about 100,000 individuals are waiting at any given time, yet the number of available organs falls tragically short. For many, the wait is simply too long. It becomes a race against time that not all will win. This growing demand for organ transplants far outpaces supply, leading to a global healthcare challenge. Medical advancements have made transplants a lifeline for those with failing organs, yet the limited availability of donated organs remains a critical bottleneck. The shortage isn't merely a numbers game, it's a complex web of ethical, logistical, and medical challenges. Enter 3D bioprinting, a realm where innovation meets biology. This technique holds the potential to revolutionize organ availability. By using a layer-by-layer approach with bioinks composed of living cells, researchers are not just imagining, but actively working towards creating functional tissue structures. Yet the path is fraught with scientific hurdles, as the complexity of producing fully functional organs remains a formidable challenge. Could these visionary technologies bring us closer to a future where organ shortages are a relic of the past? As we delve into the next chapter, we'll explore the remarkable strides and the obstacles that stand in the way of this groundbreaking frontier. 3D bioprinting is an extraordinary intersection of biology and engineering, aiming to replicate the intricate tissues and organs of the human body. Essentially, it uses 3D printing-like techniques to combine living cells, biomaterials, and bioinks, liquid mixtures that provide essential nutrients and support, to craft complex tissue-like structures. These methods, rooted in a layer-by-layer approach, begin with high-resolution imaging technologies like CT and MRI to create precise models for printing. Whether it's fabricating tissue models for drug testing or exploring applications in biosensing and environmental remediation, this technology is rapidly evolving. The process doesn't stop at building the tissue structure. Post-bioprinting steps are crucial, involving bioreactors that simulate the dynamic environment of the human body to nurture and mature these tissues. Despite the potential, translating these constructs into functional organs for human use remains a challenge, particularly due to the need for working blood vessels and the sheer number of cells required. As we advance, approaches like biomimicry and autonomous self-assembly offer promising paths, aiming to imitate natural biological processes or use miniature building blocks. But how close are we to fully functional transplantable organs? In the next chapter, we'll navigate the hurdles and breakthroughs shaping the journey from bioprinted structures to living, breathing organs. In the realm of 3D bioprinting, the journey from concept to creation unfolds through a meticulous three-step process: pre-bioprinting, bioprinting, and post-bioprinting. Each stage plays a crucial role in the construction of functional, tissue-like structures. In the pre-bioprinting phase, it all begins with creating a precise digital model using advanced imaging technologies like CT and MRI. These images guide the preparation of bioinks, a delicate blend of cells and nutrients that will soon become the building blocks of new tissues. The accuracy of this digital blueprint is paramount as it dictates the outcome of the entire process. Next, in the bioprinting phase, the magic begins. Here, the bioinks are meticulously deposited layer by layer to form 3D structures. This stage mirrors nature's own assembly line, but with room for innovation. Although functional artificial organs such as livers and kidneys can be crafted, challenges remain, notably the creation of intricate networks like blood vessels crucial for nutrient distribution. Finally, the post-bioprinting stage secures the stability of these creations. Through mechanical and chemical stimulations, along with cutting-edge bioreactor technologies, tissues mature and become viable for potential transplantation. As we explore this intricate process, the next chapter will reveal how these engineered tissues might soon transform into living, breathing organs, bridging the gap between science fiction and reality. Yet, as we delve into the challenges of bioprinting organs, the journey from printed structures to fully functional organs is anything but straightforward. One primary hurdle is replicating the complex vascular networks that naturally occur in human organs. These networks are crucial for delivering oxygen and nutrients deep within the organ, without which bioprinted tissues cannot survive. Moreover, the sheer volume of cells required to mimic the density of real organs is staggering. The process demands not just billions of cells, but also highly precise organization to ensure these cells function harmoniously. Technologies like photolithography and magnetic 3D bioprinting have emerged, offering diverse methods to address the stability and viability of cells. However, achieving the intricate balance of various cell types, each contributing to the organ's function, remains a formidable task. Post-bioprinting, maintaining the structural integrity and mechanical function of these creations is critical. Bioreactors, for instance, have shown promise by simulating natural conditions, accelerating tissue maturation, and fostering necessary vascularization. Yet the question remains, how do we translate these engineered tissues into viable organs that can thrive post-transplant? In the next chapter, we'll explore the cutting-edge bioreactor technologies that may hold the key to this complex puzzle, potentially ushering in a new era for organ transplants. Bioprinting, in its pursuit of the extraordinary, ventures into the realm of biomimicry. Here, the aspiration is both simple and profound, to recreate the exact architectural elegance of human tissues and organs. This approach, known as biomimicry, seeks to mirror not only the shape and framework, but also the intricate microenvironment that constitutes natural tissues. By delving into this microscale, scientists aim to replicate the precise organization of cells and the accompanying extracellular matrix. The challenge lies in duplicating this complexity, requiring a thorough grasp of the biological forces at play within these environments. Researchers must understand the natural solubility factors and the extraordinary organization of functional cell types. Only then can we attempt to recreate the cellular and extracellular components that make up our organs. While the potential is enormous, the journey is fraught with challenges, as the exact duplication of these structures is imperative for success. This is where the marriage of technology and biology becomes truly vital. But as we delve deeper into these microscopic blueprints, the question arises, how can we ensure these bioprinted tissues thrive beyond the lab? Join us next as we examine the revolutionary role of bioreactor technologies in nurturing these living creations, bridging the gap from printed prototype to functional transplant. Autonomous self-assembly takes inspiration from the mysterious elegance of embryonic development, a natural process where cells instinctively come together to form the intricate tapestry of life. Here, the blueprint isn't just printed, it's encoded within the cells themselves. As they embark on this journey, cells in their nascent stages create their own extracellular matrix and arrange themselves according to innate signals. This process is not about imposing a design from the outside, but rather allowing cells to self-direct, mimicking the early stages of organogenesis, where tissues naturally emerge. In this scaffold-free model, self-assembling spheroids organize and fuse, mirroring the dynamic choreography observed in embryonic growth. Through precise cell signaling and patterning, the inherent biological functions and microarchitecture essential for complex tissue structures are achieved. This approach requires a profound understanding of the mechanisms that drive embryonic tissue development and the microenvironment they inhabit, harnessing the cell's intrinsic capabilities as the fundamental architects of life. As we delve deeper, the potential of these autonomous processes to yield functional bioprinted tissues becomes ever more tantalizing. But how do we ensure these living structures survive beyond the lab bench? Next, we explore how bioreactor technologies nurture these nascent creations, poised to revolutionize the landscape of organ transplantation. Arise small functional units known as mini-tissues. This innovative method marries the precision of biomimicry with the inherent natural processes of self-assembly. By mimicking the intricate microarchitecture of human tissues, researchers create tiny functional tissue units that can self-organize into larger, complex structures. These mini-tissues serve as the building blocks, each tailored to replicate the specific characteristics of their natural counterparts. Imagine them as biological Lego pieces, each piece meticulously designed to fit together seamlessly, guided by the natural cues embedded within their cellular structures. The fusion of these mini tissues into fully formed organs represents a quantum leap in our ability to engineer life-saving medical marvels. This cutting-edge combination not only enhances the structural integrity of the bioprinted organs, but also improves their functionality, making them more viable for transplantation. By understanding how these mini tissues connect and thrive, scientists edge closer to constructing organs that are virtually indistinguishable from those that nature has perfected over millennia. But how do we ensure these complex creations are ready to function in the human body? In our next chapter, we'll delve into the bioreactor technologies that are crucial for nurturing these nascent structures, preparing them for their ultimate test, transplantation into living beings. As we look toward a future with 3D printed organs, the promise of personalized medicine becomes more tangible than ever. Imagine crafting organs tailored specifically to an individual's unique biological makeup. This isn't just science fiction, it's a burgeoning reality made possible by the precise techniques of 3D bioprinting. By utilizing a patient's own cells, the risk of organ rejection could be significantly reduced. This personalized approach holds the potential to address the chronic shortage of donor organs, offering a lifeline to those on lengthy transplant waiting lists. The use of bioprinting extends beyond mere organ creation. Researchers are also developing methods to precisely replicate the complex microenvironments and tissue structures found in nature. Techniques like biomimicry and autonomous self-assembly allow the creation of living tissues that can integrate seamlessly into the human body. Although challenges remain, such as replicating the intricate network of blood vessels and ensuring the survival of transplanted tissues, ongoing advancements continue to push the boundaries of what is possible. As we stand on the cusp of this medical revolution, one question lingers. How soon will we see these innovations transform from cutting-edge research to routine medical practice, reshaping the landscape of healthcare forever?